Welcome everyone to the webinar series of the 8th Language Technology Center here in the Basque Country. This is the last webinar in this courses series. You can see who we hosted before, and we'll close with a very exciting talk by Marco Valentino. And next year we'll also start around October with a new series, which we will announce at due time. So let me present Marco. He's a lecturer in AI and applications of AI in the NLP group at Sheffield. Prior to that, he was a member of the neuro-symbolic AI group at EDAB Research Institute in Switzerland and did a PhD in the University of Manchester. So he's developing AI systems that can use explanation, investigating the integration of neural and symbolic AI methods. So he's interested in developing methodologies to interpret, control, and evaluate LLMs with a focus on disentangling knowledge acquisition from abstract logical reasoning and enabling auto-distribution, out-of-domain generalization. So, Marco, we're really excited about your talk, so the floor is yours. I'll stop sharing.
Perfect. So let me try to share my screen. Okay, can you see the slides?
Yes, they're coming. Yeah, good.
Full screen. Okay, so thank you very much for the invitation. First of all, really happy to be here and to give this talk. So in this talk, what I'm going to try to do is to try to give you an overview of this persisting tension between what we can define as a plausible versus formal reasoning, and how basically we can think about LLMs as a way to help us reconcile this tension that persists in the field of AI, NLP, and in general. So if you have any questions during the talk, please feel free to interrupt me. And yeah, let's start. Okay, so just briefly mention that we have this recurring and persistent challenge in AI that basically refer to the integration of these two types and forms of reasoning. So from one side, we usually talk about formal reasoning when we want to basically perform a form of inference that concern the structural validity of arguments. And in this particular case, we typically care about whether conclusions follows from premises according to fixed syntactic or logical rules. So think about, for example, deductive reasoning, which is a typical form of formal reasoning, where we derive conclusions from premises by systematically applying logical rules. And then from the other side of the spectrum, we have complementary form of reasoning, which we can refer as plausible reasoning, which instead of just dealing with the application of syntactic logical rules, it deals with the actual plausibility and the content of arguments, in particular with their grounding in background knowledge, context, and domain-specific assumptions. Now, if we look at the picture on the right-hand side of this slide, we can immediately see that usually formal reasoning typically happens in purely symbolic space, so we don't really care about what is inside what is the content, the semantic content of the arguments. So this type of reasoning is kind of independent from the semantic content, while this plausible reasoning usually happen in concrete semantic space, for example, in language. Okay, and if we think about LLMs, we know that they are mostly trained within linguistic space. And so we can think about them as a really good model for plausible reasoning, but because of some features that I will explain later, they still struggle with this systematicity that is required for formal reasoning. Okay, so why do we care about integrating those two forms of reasoning effectively? Well, if we think about high-stakes domains, for example, healthcare, for example, if we position ourselves in a scenario where we have certain patients that we want to, for example, understand which type of treatment we can provide, then what we could do if we want to build an automatic system to do that, we can rely on scientific background, past clinical studies, the patient profile itself, and we could try to reason by aggregating evidence from background literature and try to compose this sort of logical derivation to help us, for example, verifying claims, hypotheses, or answering specific questions about specific patients' conditions, right? Now, if we think about this, the type of reasoning that is required to do this kind of derivation, well, they combine elements of both aspects, right? So we need to be able to ground those evidence in background literature. So there is a dimension of plausibility and contextual relevance, but there is also a dimension of systematicity. So we want a system to be able to essentially derive new knowledge that is implicit in background literature. And in order to do that reliably, we will need to apply this kind of systematic formal reasoning capabilities. So a system that is not able to effectively orchestrate and integrate these two forms of reasoning typically suffer from biases in critical domains. They tend to be sensitive to superficial patterns or problem variation, for example, and they can struggle to effectively be adapted to new domains or in general to perform abstraction and generalization. So it is really important to consider both forms of reasoning to enable AI to be deployed in high-stake domains. Now, if we look at LLMs specifically, we know that they actually suffer from these kind of limitations that we mentioned before. In particular, we know, for example, that LLMs can lack robustness and consistency, in particular if you do superficial perturbations that do not change the underlying semantic of the problem. LLMs can actually drop quite significantly in performance. So this shows that they cannot essentially deal with the systematicity required for reasoning. We know also from other studies that LLMs typically exhibit a dissociation between what they actually know versus how to deploy effectively that knowledge to perform reasoning reliably. For example, if we give LLM, if we test LLM with a set of probes that ask LLM whether they possess the relevant knowledge to address a specific task, we might find that they actually are able to answer those questions in principle. So for example, which type of reasoning you need to address this type of problems, they will be able to provide you with a reliable answer on the knowledge and the type of inference that is required. But then when tested more explicitly on the reasoning itself, they struggle to actually deploy and combine that knowledge reliably. And you can see this explicitly when constructing data set to test for this phenomena, where basically the accuracy on the knowledge probing itself tends to be quite high, but then when asking the models to actually deploy their knowledge to do inference, there is a quite significant drop in performance. So this means that the LLM kind of represent the necessary knowledge, but the reasoning mechanism can be sometimes dissociated from the mechanism used for knowledge representations. Another really famous example of these tensions in LLM is given by studies on content effects, which essentially show that LLMs tend to exhibit a bias towards plausible arguments when assessing the logic validity, formal validity of a given argument. For example, if we give an LLM a syllogistic reasoning problem, if the content of the syllogism aligns with the word knowledge, then the LLM will tend to overestimate the formal validity of the arguments, even if the connection between premises and conclusion is not formally valid. Vice versa, if we give LLMs arguments that are not plausible or grounded in background knowledge, what we observe is the exact opposite. So LLMs will tend to underestimate the logical validity of those arguments. And this type of bias is usually referred to as content effects. And it actually shows that LLMs tend to entangle this notion of plausibility with the notion of formal logical validity. And we also have mechanistic evidence supporting this, which show essentially that we can reliably extract mechanism or circuit, as they are referred to in mechanistic detectability, that explain symbolic reasoning behavior in LLMs. But then these same mechanisms tend to be easily corrupted when we instantiate, for example, a reasoning problem such as syllogism with counterfactual examples. And then again, this is a direct mechanistic evidence that tells us that LLM can somehow learn the mechanism for formal reasoning, but these mechanisms tend to be essentially corrupted by background knowledge. So there is an entanglement going on. Okay, so we have seen then essentially LLMs are a really good model of plausible reasoning, that they can somehow represent some of the mechanisms for formal reasoning. But then the question becomes, okay, how can we actually reconcile these two words? And what I would like to do in this talk is giving you an overview of two sides of the spectrums, focusing on one side on more symbolic representations, so where the idea is essentially leveraging the LLM, but confining LLMs to the dimension of plausible reasoning, and then going in the direction of more symbolic representation, more symbolic explicit logic. And one example of this, so the extreme of this, is actually this kind of hard neuro-symbolic integration that I'm going to talk about. And then we have the other side of the spectrum, which tries to go more in the direction of distributed representations, so try to essentially bring formal reasoning inside LLMs themselves. And in particular, we would see a transition from hard neuro-symbolic integration towards more activation level interventions to try to improve formal reasoning. And there is typically a tension between the two. So if you move towards the symbolic spectrum, then you gain high verifiability, you gain formal guarantees, but you also sacrifice a bit of flexibility and scalability. On the other side, you might lose a bit of verifiability and formal guarantees, but you gain in flexibility and scalability. So as we will see, there is an actual trade-off between the two that I would say really depends on the type of applications that you care about. Okay, so let's start from the hard neuro-symbolic area. Okay, so what is the main idea behind this? So essentially the idea is to leverage the linguistic capabilities of LLMs. Okay, so we know LLMs are really good models for language. They are able to actually translate between different patterns and formats. And so the really basic idea of this is basically, let's leverage LLMs to deal with almost like as a natural language interface. So we use LLMs to deal with natural language, with problem specification, but then we delegate the reasoning execution to an external symbolic solver. So a typical architectural pattern of this looks like the figure that you can see in the slides. So you typically use the neural components of the LLM to do what's known as auto-formalization, so translating natural language into a formal language. And then you entirely delegate the execution of the logical reasoning to an external symbolic solver, which could be a Turing prover, could be a Python interpreter, and so on. And the idea is that by leveraging the symbolic solver, we can actually gain formal derivations that we know are systematic and robust. And of course, one crucial point for this is the step of auto-formalization, which is a research direction in itself, where the problem is essentially summarized in this example. So we start from a problem expressed in natural language, in this case, a Turing proving problem. Then what we want is to get a formal code as output. And then once we have this, we essentially can leverage an external Turing prover such as Isabelle or Lean to do the verification and the proving itself. Okay, so a typical example of this architecture is provided by this approach, which is called LINK, which is one of the early methods trying to essentially leverage the power of LLMs to perform this kind of hard neuro-symbolic integration. And as you can see here, the architecture is really simple. So if you have a syllogistic reasoning problem, for example, you simply perform semantic parsing, which corresponds to the auto-formalization problem. Then you might want to do this multiple times to deal with the essentially with the non-deterministic generation typical of LLMs. Then essentially once you have your problem formalized, you use a logic Turing prover to derive the entailment, for example, in this case. And then what this approach does essentially is using a majority voting approach to decide the final label. Okay. And these tend to work pretty well for simple logical reasoning tasks. In particular, the authors here show that their model LINK can significantly outperform chain of thought methods and zero-shot approaches, essentially. Okay, this sounds great. However, it is also a bit simplistic in a way, and it possesses several limitations. In particular, as we have seen before, in this really basic neuro-symbolic integration, we are kind of really confining LLMs to simple language interface. But there is a critical problem here, which is that most of the time when dealing with natural language problems, the problems tends to be underspecified, okay? And actually this is a quite deep issue when dealing with neuro-symbolic integration, because if your problem is underspecified, then simply translating it into a formal language will not work, because the logical solver and the symbolic solver in general will need to have a completely specified problem to actually do their job. Okay, so the idea actually is that we can move in a direction where we use a bit more the power of LLMs, not simply as a language interface, but also as a plausible reasoner that is able to deal with background knowledge, and it's kind of able to extract implicit information from unspecified problems. Okay, and so the idea is that instead of having this unidirectional communication between the LLM and the symbolic solver, we can actually establish an iterative refinement process where the LLM doesn't act anymore as a simple language interface, but also acts as a plausible reasoner using abductive inference to essentially add knowledge to unspecified problems. Okay, or for example, to generate a natural language explanation that can support a more challenging reasoning problem itself by a chain of thought, for example. Then once the LLM performs this kind of initial reasoning, we can consider this initial reasoning as a candidate solution, right? And at that point, then we can perform auto-formalization, give the problems to the symbolic solver, but then the symbolic solver itself can be used to provide feedback to the LLM to iteratively improve the solution. So imagine, for example, you start from a complex problem. The LLM will initially provide an explanation. We'll do the auto-formalization. Then this auto-formalization will be given to a logical solver. The logical solver might not be able to find a proof because the problem might be challenging or because of inconsistencies introduced in the LLM explanation, for example. But then the power of this approach is that the logical solver can explicitly provide feedback to the LLM to tell where the reasoning is actually failing or where the proof cannot be found. And then the LLM itself can actually correct the explanation, refine it, and establish this kind of iterative refinement loop until a valid logical explanation can be found. Okay. And this approach. Is that a question? I can hear some noise, sorry.
Yeah, it seems it was somebody with noise.
Okay, no worries. I will keep going. Okay, so and so basically here the idea is that most of the time when dealing with natural language problems, we might have some underspecified premise or condition, right? An example of this can be, for example, natural language inference, textual entailment, question answering, where usually you have like a single premise and an hypothesis, but the intermediate step to actually derive the hypothesis logically are actually hidden and needs to be made explicit via the generation of a natural language explanation. So in this case, we can think of the hypothesis itself as a theorem that we might want to prove, but then the original premise and the explanations become the assumptions and the axioms that we might want to use to actually prove that theorem. So there is a one-to-one correspondence that can be found between natural language explanation and this kind of neuro-symbolic integration. So if we want to then instantiate this paradigm in practice, a typical system might work like the one shown in this figure. So we start from an underspecified problem. Let's say we have a premise, we have an hypothesis, we might have an initial explanation that can be, for example, annotated by humans or generated by LLMs themselves. Then what we can try first is to do auto-formalization, check if there are any syntactic errors introduced during the auto-formalization. But then we can leverage LLM to do what we call as a rough inference, so which essentially corresponds to this idea of leveraging LLM for plausible reasoning, right? So the LLM can give us the steps that are required to actually infer the hypothesis. After this, we can do auto-formalization and then leverage the theorem prover to check whether the explanation itself can be logically verified or not. If that's the case, then we have a valid explanation. Otherwise, we can use the feedback from the LLM, from the symbolic solver, sorry, to essentially start this refinement loop. Okay, so how does it work in practice? So we did some experiments on data sets containing natural language explanation of increasing complexity. What you actually can see is that the iterative refinement method is actually quite effective in improving the logical validity of explanations. In this particular work, we start from explanation annotated by humans, and then we use this kind of iterative refinement to see if the combination of LLM plus symbolic solver can make this explanation logically valid and complete. And you can see the trend quite clearly here across datasets. So there is a quite consistent and substantial improvement across all the datasets that we try. However, you can also see that the effectiveness of the method actually depends also on the complexity of the dataset. So on the left-hand side, we have ESNLI, which it's a simple textual entanglement problem that typically includes a single step explanation. And as you can see, the performance here towards the end of the refinement tend to be above 80%. However, if we move to more complex domain, for example, towards word tree, which is a scientific question answering problem that requires multi-hop reasoning with really long explanations, we can see that the number of verified explanation at the end still tend to be relatively low, so significantly better, but still relatively low. In addition, we also found that there is quite a large gap between large models, so proprietary models and open source models, in particular in the auto-formalization problem, in the auto-formalization step. You can see, for example, in the figure on the top, the number of syntactic errors spread across open source models versus GPT-4. And you can see that GPT-4 clearly outperforms open source models. However, what we found is that if you disentangle textual inference from auto-formalization, for example, using GPT-4 for auto-formalization while leveraging open source models for textual inference or plausible inference, we found that this can improve quite substantially performances. So in general, this kind of integration works, but still struggle to deal with really complex explanation, a bit because of the auto-formalization bottleneck, but also because of the capability of LLMs to effectively self-refine. Okay, so I want to give you also an example of how this kind of neuro-symbolic refinement approach can work for high-stakes domains. In this particular example, we tried to use this approach for clinical trial matching. So the idea is that, so the problem is that you have a patient profile with certain characteristics. So you have you might have age, gender, previous diagnosis, and so on. And then you have a clinical trial, which is clinical trials are new studies to test the efficacy of newly introduced drugs, for example. And one of the problems is actually given a new clinical trial study, so given the eligibility criteria, trying to actually find the right set of patients that are actually eligible for the treatment. And of course, for this type of domains, simply using LLMs might lead to high unreliability. And so the idea is actually that we could leverage this kind of neuro-symbolic approach to make the decision more systematic and explainable for the end clinicians. And what we did in this work was essentially instantiating the neuro-symbolic pipeline that I was describing before, but for clinical trial matching, using LLM to deal with the unspecified patient profiles or implied clinical knowledge, while delegating the final matching to a constraint satisfaction solver, in particular Z3. And what we can find here is that essentially this kind of abductive-based neurosymbolic refinement tend to work much better than chain-of-thought reasoning or zero-shot approaches, but also tend to be more robust when compared to more basic non-abductive neurosymbolic setting, such as link, for example. And this because real-world domains typically have a lot of unspecified knowledge that needs to be made explicit by the use of background knowledge as well. Okay, so just to finalize this part, I want to mention that the direction for this kind of hard neurosymbolic integration is to move towards a multi-reasoning paradigm or an adaptive approach. One of the limits of the methods that I mentioned so far is that they typically tend to specify in advance which is the type of logical solver that you might want to use, or which is the type of logical formalist that you might want to have. However, when dealing with real-world problems, you might need to integrate your LLM with different type of solvers. So different type of solvers might be suitable for different type of problems, or you might have situations in which a single problem might require sequential integration or composition of different reasoning paradigm. And so the direction that we are now seeing across the hard neurosymbolic integration is to move more towards agentic pipelines where the problem is first decomposed into different sub problems, and then we have a sort of a planner that can integrate together multiple solvers according to the different problems that needs to be solved. And this, of course, seems to work much better than having like a static neurosymbolic integration. And the same thing can be done with respect to the logical formalism itself. For example, if you are dealing with common sense reasoning, then using first order logic might be the most appropriate thing to do. However, if you are dealing with other types of reasoning, such as ethical reasoning or deontic logic, you might want to use different type of formalism. And it is quite clear from recent work that essentially the choice of the formalism itself can have a quite substantial impact on this ability of self neuro-symbolic refinement. As discussed before, one of the key limitations or central bottleneck of this approach is essentially the auto-formalization part. So essentially, it's like instead of delegating the reasoning part, so the challenge of the reasoning part to the LLM, what we are now doing is essentially transferring the complexity of the task within the auto-formalization framework. And so one question we might want to ask is, what is the limit of this auto-formalization with current LLMs? And one way to do this is actually to test auto-formalization in more realistic setups, such as mathematical definitions or mathematical statements extracted from real-world scientific papers or textbooks, for example. And you can see how usually the real-world statement extracted from papers or scientific texts or textbook tend to be much more complex than the one we have in current benchmarks. And unfortunately, what we see is that when we actually instantiate this auto-formalization pipeline with self-refinement and test it on real-world statements, much more complex statements, for example, in the mathematical domain, we can see that we still have quite significant drop in performance. There is still some improvement that is given by the refinement loop, but I would say that auto-formalization capabilities are still confined to benchmark more than to real-world problems. And so if we need to summarize the overall limitations of these neuro-symbolic integration, is that, of course, auto-formalization for complex real-world problems represent a major challenge. So this is an entire research direction, so trying to understand how to do auto-formalization properly. We might also introduce scalability issues if, for example, we integrate highly expressive logical solvers. And also we have seen that small language models in particular still possess limited formalization and self-refinement capabilities, which might impact concrete applications with open models, for example. Okay, so we can proceed to the next step. Just want to check if there are any questions on this first part. Okay, so I will proceed. Okay, so we have seen one side, the extreme side of the spectrum, so the idea of integrating large language models with formal logical solvers. What I now want to discuss about is something in between, where the idea is basically trying to get rid of the symbolic solver and the bottlenecks that it introduces, such as this kind of hard formalization requirements, and then essentially trying to see if we could still leverage symbolic representations, but entirely using large language models. Okay, the idea here essentially use exactly the same pipeline that I was discussing before, but now each of the individual steps are performed by the LLMs themselves, including the step of verification and refinement. And one example of this is symbolic chain of thought. And as you can see here, basically, the idea is that we might want to use symbolic representation extracted from natural language to mitigate some of the challenges that we have discussed before, such as content effect, for example, or this conflation and entanglement between plausible and formal reasoning. And so the idea is that we start from our natural language problem. We might generate a chain of thought reasoning, but then the idea is that instead of generating a chain of thought reasoning entirely in natural language, we can ask the LLM to directly generate the chain of thought using a symbolic language, such as first-order logic, for example. And what previous work has shown is that this mechanism can actually be quite effective in improving the reasoning performance across a range of logical reasoning tasks. In particular, what previous work has shown is that symbolic chain of thought can outperform basic chain of thought reasoning. And there are other ways to actually do this by exploring a bit of tension between how much natural language you want to have in your chain of thought versus how much symbolic components you may want to have. So there are many different design choices that one can adopt and apply. But usually the pipeline works like the one shown in this slide, where we have a problem, we have an abstraction process where we essentially abstract from the concrete semantic content of text, and then we use that to let our LLM reason on more abstract representation. And this again seems to work pretty well also in dealing with adversarial perturbations that can be introduced to check the consistency and reliability of LLMs. Some other work have tried to extend this idea by using symbolic tasks and symbolic reasoning trajectories extracted using symbolic chain of thought to essentially provide a deeper supervision or process supervision for LLM-generated explanations. And then again, the message here is that by leveraging symbolic representation directly integrated into chain of thought reasoning, we can actually improve quite significantly the reasoning capabilities of LLMs, as well as the efficiency in fine-tuning, but also in generalization across domains. So in general, we might be happy essentially with a compromise, especially if we can sacrifice a bit of rigor and formal verifiability for flexibility. At the same time, we need to keep in mind that when we actually remove the solver from the picture, we might improve the capabilities of LLMs, but some of the fundamental challenges, such as the potential inconsistencies introduced by LLMs, can still remain. And especially the faithfulness of our reasoning and the ability to explicitly and deterministically verify it might not be guaranteed. Okay, so just to finalize the talk, then I would like to move towards the other side of the spectrum. And the idea here is basically to completely ignore any sort of symbolic representation, explicit symbolic representation in language, in text problems, chain of thought in general, and trying to intervene directly within the activations of the LLMs. So, and the idea here is essentially to try to perform a sort of latent space disentanglement between plausible and formal reasoning within LLMs themselves, potentially trying to inject some sort of formal control by directly intervening inside the representation. So the hope here is that if we can do some sort of if we can do some sort of intervention within the geometric space and the circuits that are used by LLMs to represent formal and plausible reasoning, we might be able to obtain a more disentangled representation and more controlled inference in general. And the hypothesis behind that is essentially derived a bit from the mechanistic evidence that I was discussing at the beginning of the talk. So the hypothesis is that symbolic reasoning circuits are actually learned implicitly by the models, and we know this because of mechanistic studies. However, they get contaminated by contextual knowledge and plausible arguments when basically encountered in natural language. Okay, so the idea here is that if these symbolic circuits are actually inside the model, we should be able somehow to intervene to disentangle a bit more those circuits from the knowledge representation itself. And hopefully this should give us better formal reasoning capabilities. And one way to try to disentangle these two is essentially using a technique known as activation steering. Okay, and the assumption behind this is exactly the one I mentioned before. The idea is that formal reasoning might be actually represented into a linear direction within the models, but then for some reason, because of the uncontrollability of the model itself, these kind of capabilities are corrupted when encountering counterfactual arguments, for example. So if this is the case, then we can employ a steering vector to actually try to elicit a bit more formal reasoning inside the models. Okay. So the way activation steering works is basically in two different phases. So in the first step, what we do is to collect what are known as steering and condition vectors. In particular, the condition vectors are based on a set of training examples for which we know the label of, right? So imagine, for example, you have a syllogistic reasoning problem and you know whether the problem is logically valid or not from a formal point of view. So we might want to collect condition vector to establish whether and when to do intervention inside the model, so to check specific internal conditions within the model. And then on the other side, we might have steering vector, which are actually based on the behavior of the model, so whether the model is actually behaving as expected or not. Okay, and so if the model is actually behaving as expected, so it's actually doing formal reasoning as we want, we might consider this internal activation as positive steering vectors. Otherwise, we might consider them as negative steering vectors. Okay, so in this initial phase, we collect a set of training examples, we run them through an LLM, and then we check and collect the internal activation, check the examples and the behavior of the model, and then split them between condition and steering vectors. Okay. Once we have this collection of activations, then we can actually use them at test time to essentially steer the models towards the desired behavior. Okay. And the way this works is basically to go through a conditional steering approach. So the idea is that you have your test example, you give it to the model, you check the internal activation of the model before outputting the answer. Then you compare it with your condition vectors to determine if you might want to steer it or not. depending on how they deviate from the condition vectors themselves. And then you essentially use the steering vectors to compute a direction, a linear direction that you might want to use to steer your model. And the way it works, basically, you take your positive steering vector, you basically pair them with the negative steering vector, and you compute what is called as a contrastive steering vector. So the idea is that you subtract from the positive steering vector the negative steering vector, and then you average across the pairs that you have. And this basically gives you an average optimal state and direction where the LLM should be within its internal activation state. And so what you do is to leverage this desired direction to steer the model by applying a sum, essentially by summing the internal activation of the model with the contrastive steering vector that you derived, given a specific strength that you can define, for example, using the condition vectors. Okay, so and what we see by looking at experiments is that activation steering actually is quite effective to improve formal reasoning and to mitigate the content effects and biases. You can see it quite clearly in this figure. In particular, on the left-hand side, you can see how the accuracy of Llama 1 billion improves when changing the strength of the intervention for steering. We can see that basically with the non-zero strengths values, the accuracy in formal reasoning can improve quite effectively. And while we improve accuracy, we are also able to essentially bring content effect to zero. So the model is not anymore biased towards plausible or implausible arguments. One question is to what extent actually these activation steering methods can generalize across prompt variations, across problems, and especially across languages. We did some follow-up work in which we actually asked that question and tried to see what happened. What we found is that, in particular for formal reasoning and for syllogistic reasoning, activation steering seems to be quite robust to prompt variations. So if you collect your steering vectors using a specific prompt, but then you apply it at test time with different prompts, we can see that despite some fluctuations, the desired steering can be still achieved. So we can still improve accuracy, and we can still quite effectively minimize reasoning biases. And in a recent work presented at TSL, we also showed that steering can quite effectively generalize across different languages. So what we did was collecting steering vectors entirely in English and then apply them on reasoning problems in other languages. What we found is that there is a quite effective cross-lingual transfer that happens. And this kind of suggests that there might be some underlying language agnostic mechanism that can be elicited in LLMs to actually improve formal reasoning beyond any specific language. We also checked whether this can generalize to different auto-domain tasks. And here the results were quite mixed. So we found that for some tasks that are really related to syllogistic reasoning, steering can transfer quite well. However, for other tasks, this is not the case. So we actually need additional studies to understand how to effectively generalize across tasks. And we also found this to be quite model dependent. So Llama and Gemma seems to generalize a bit better. Llama and Quen seems to generalize a bit better, while Gemma tends to be more susceptible to the specific steering vectors that we actually extract. Okay, so we have seen a bit of the...
Sorry to interrupt.
Yes,
Just Mark, just to let you know that we are 3 minutes from the
yeah, I finished. I'm just summarizing.
Okay, no problem. Just to let you know, just in case.
Yeah, so just a summary. So we have seen the spectrum, the full spectrum of methods that can be used to try to reconcile plausible and formal reasoning in LLMs. We have seen also that there is a tension between the two. So if you care about more verifiability, then more symbolic representation probably is the way to go. While if your application demands high flexibility and scalability, we have seen that quite significant results could be also achieved by directly intervening within the models themselves. Okay, so what's then the future direction? Well, there are a couple of them. So I believe what we should try to do as a field is to move towards a more unified, disentangled representations between the formal reasoning component and the plausible reasoning. So what we saw from recent work is that LLMs, because of their monolithic architecture, tend to entangle the mechanism for reasoning and knowledge. However, I think there are some nice directions that the community has started to explore to try to disentangle a bit more these two dimensions. One example of this is the hierarchical reasoning model, which explicitly separate this notion of fast, plausible reasoning from slow, more deliberate or logical reasoning within the recurrent LLM transformers architectures. There are also some nice directions that tend to use modular architectures such as mixture of experts to try to explicitly disentangle the word knowledge linguistic capabilities from logical reasoning. And finally, I think there is some interesting opportunity to try to use symbolic feedback from theorem provers to actually provide direct signal for training LLMs via, for example, reinforcement learning. Okay, this is the end of the talk. So thank you again for the invitation. So I'm happy to answer any question.
Thank you, Marco. So now we have a few minutes for questions. Anybody? You can raise your hand or just take the mic directly. So I do have, yeah, hello? Oh, that's nice. Okay, I do have a general question. So in a way, the hard neuro-symbolic integration looks like more desirable in theory, right? Because you can have it's verifiable and you can have guarantees. You can decouple, as you were mentioning by the end. You can decouple what's the semantic content and what's actually the reasoning part, right? And I wonder if, so which is the bottleneck? Because this is the part where you spend most time and then kind of seems a bit like in a dead end. I don't know, it's not dead end, it's not perhaps the best description, but it's hard. And I was wondering whether the bottleneck was that the theorem provers don't have enough rules about what they are reasoning about, right?
Yes.
It's a prerequisite for them to do a good job, right?
Yes. So from my point of view, I think the hard neuro-symbolic integration is the way to go, especially if you care about reliability and systematicity, right? So I think it's the way to go for high stakes applications because they provide this kind of formal guarantees. The problem with auto formalization is, I think it's a bit, I think basically the problem is that we are trying to integrate completely different words here. So the LLMs still struggle with formalizing complex knowledge effectively. Okay, so there is the LLM component that I think is still limited in its capability to do reliable auto-formalization, especially for complex real-world problems. From the other side, you have the theorem prover that expect to have a full reliable formalization. So you can think of the theorem prover almost as like a set of piece of puzzles that needs to be there to make it work, right? So, but the LLM tend to be a bit conservative on that. So when you integrate them, you tend to have some missing knowledge that prevents the theorem prover to actually work effectively. Another issue is that LLMs might still hallucinate when doing auto-formalization. So, for example, making sure that your formalization is actually semantically equivalent to the original natural language problem is really hard to check, right? So because the theorem prover can tell you if there is any syntactic error or if it's not able to find a proof, but it cannot tell if the formalization itself is actually faithful to the original problem that you're actually trying to solve. So essentially here the problem transfer entirely into the auto-formalization. So it collapses into the auto-formalization problem itself, which is a huge research direction in itself, basically.
Thank you.
So I don't know what is the actual solution for that.
Yeah, we wish. Do we have time for another question? I do have another one if nobody wants to take the floor. Okay, so the other one is a bit more general and is linked to this issue we have now in academia with LLMs, is that the frontier labs are going one step, to put it softly, one step ahead, right? So I realized that I think it was slide 4.
Yeah.
You were, maybe it's not necessary to show it, but there was a big spread of error or accuracy.
Yeah.
Modern models and the frontier model at the time, which I think was GPT-4o, I'm not sure.
Yeah.
Which had a very, very small error.
Yeah.
So I was wondering, and also because we now know that in these frontier labs, they are able to solve math Olympiad problems, and also that, some they found proofs for some theorems which haven't been proved for now. So I was wondering whether this is a matter that has not been solved, but have not been made big steps in those frontier labs, which they haven't published, I think. So I don't know, I was wondering, so is this maybe solved in quotes? Are they 2 steps ahead, so they kind of have a solution which we haven't seen?
So I think for sure there has been a huge improvement, especially in frontiers models. As I mentioned briefly, now the auto-formalization itself is not anymore done by a single model, but now you have this kind of agentic system, right? So which can go quite far. But I think the bottleneck is still there. So the idea is that you still need to pre-train this really huge model to make it work, is something that probably in academia we should try to challenge a bit more. Okay, so I think the solution is probably trying to explore architectures that are a bit more modular and that are more data efficient themselves. So of course, if you try to use an open source model and a smaller one to compete with Claude, it's probably not going to work, right? But I show at the very end that there are some nice direction that I think for us in academia is probably the way to go. So the idea to really try to have this kind of disentanglement between different capabilities. And in particular, these hierarchical reasoning models seems to be quite effective. I think there was a really recent release where they try to apply these into language pre-training. And what they show is that the models is much more data efficient, can achieve really good performance that are comparable with the state-of-the-art approaches, but with much fewer training data. Okay, so what I believe is that, okay, probably the frontier labs might have found a good solution to improve this kind of neuro-symbolic integration and auto-formalization, but still the bottleneck in terms of data efficiency and what we would like to have for real-world application are still far to reach. So I think as academic, we should probably try to focus a bit more on having like less brute force approaches, let's say.
Okay, thank you very much. So I think we can close the seminar now. I'm very happy to have had you as the final talk in this series. So I invite anybody who's interested to follow our website for new editions next year, where we will start with another seminar series. Okay, so thank you, Marco.
Thank you very much. Bye-bye.
Okay, bye.